All right, so this is a DE. I'm supposed to solve this. Solve, okay? So the first thing you do when you're solving a DE is you start by assuming it has a power series solution. So solution. So you start by writing it like this. Y equals infinite sum. So this is the solution to the DE, and you just assume that it's a power series. So you start at 0, you go to infinity, and then c sub n, x sub n. So you always start like this by letting y be equal to an infinite sum every single time, right? Every single time. Okay, so you start by doing that, okay? So let y be equal to an infinite sum. And then you have to take the derivative of this, because you have to basically take this and then just plug it into the DE, right? So when you take the derivative of this, you have y prime, infinite sum, as n runs from, and here's the tricky part. So we'll deal with this in a minute. This is a constant, so it hangs out. This derivative, you just put the n in the front. So you get n, oh, almost messed up. C sub n, n x to the n minus 1, because you're subtracting 1 when you take the derivative, right? You subtract 1 from the n. The only issue is this. What does this start at, right? What is this number? Well, here's the thing. If you, yes?
Is C a constant?
It's a constant. So it just kind of hangs out. Good, Matthew. It's a, hey, Josh, all right, you look different. Good. So C sub, yeah, it's a constant, so it hangs out. Then you put the n in the front, and then you subtract 1, so you get x to the n minus 1. So this is the trickiest part for most people. So if you think about it, I'm going to erase this, but I'll write it down for a sec. If you plug in 0, you get C0. You plug in 0, you get x to the 0. Then you add, and then you get C1x, then you add, etc. So here you just get C0, because x to the 0 is 1, and you get C1x, then you add, etc. I'm going to erase this in a minute, but this is just for just show you what happens. So this is this. When you take the derivative of this piece, c sub 0, it's a constant, right? So it goes away. So when you take the derivative of this, the 0th term goes away. So that means you have to start this at 1, okay? So that's the key. So whenever you take a derivative, you just shift it up every time, actually. That will work every single time in this class, on these problems. So because it starts at 0, you have a constant here, c sub 0. The derivative of a constant is 0, so it goes away. So you just start at 1. So any questions on that step? If you were to do it again, you would do the same thing, except what do you think you would start at if you took a derivative? 2. Yeah, that's the most important thing. And these steps are the same, okay, for every single DE. Yep?
You get n squared. Cn n squared.
You know you would get, I'll just do it, but I'll erase it. Okay, so let's just do it. Good question. So you'd get n equals 2. We'll probably be able to do 1 today. Like, oh, that'd be awesome. They're really hard, like the harder ones. They're long. You get n minus 1, x to the n minus 2. Yeah, you would get, yeah, good question. Good question. So if you took it again, you would do that. But you don't have to, right? Because this is order 1. It's the first derivative. Okay, so I'm going to erase this. So now we plug this into the DE, right? We take this. I'm going to cross this out. We don't need this. We take these and we plug them into the DE. Okay, so we have y prime, so that's going to go here. So infinite sum, n equals 1 to infinity, c sub n, n, x to the n minus 1. That's just the y prime, right? That's just the y prime. This is tough. This is tough. I did that in my night class. We finished the whole semester, and they were like it's really tough. Minus 5. We actually went overtime. We did this for 3 hours. It was ridiculous. So 5, infinite sum, n equals 0 to infinity. Right now we're going to use this one. Right? We're going to plug in y here. So this will just be c sub n x to the n. You see it? C sub n. Oh, it's good. Oh, someone's here. Hey!
How are you supposed to solve it by putting an infinite sum in?
Huh?
How are you supposed to solve it?
You'll see. You'll see. So you assume it's an infinite sum, you plug it in, and then we're going to find the c sub n's. We're going to find a pattern for them using skills. Good question. Yeah, I know it's pretty ridiculous. Any questions up to here? Any questions up to here on any of the steps? We got time. We got to make it count. So, okay. So now this is the last thing we did last time. We have to make all of these the same. Remember that example we did? So you start by calling this k. So k is equal to n minus 1. So k is equal to n minus 1. So you do that. And then you just solve for n, right? So you would just get n equals k plus 1. I think I did that right? Added 1 to both sides. Brian, I think I have your test, Brian. Or did I give it to you? Not yet. I'll give it to you. Okay, I'll give it to you. I saw your name. I was like, oh, Brian. Oh, and then this is kind of silly. This is just going to be k. I like to do it. This is kind of ridiculous, but why not? K is equal to n is equal to k. So we've done nothing. I like to do it to be consistent, just as it's kind of psychotic. It's like, oh, it's meaningless, but we're just going to put a k here instead of an n. All right, good stuff. So now we're going to make the substitution. So let's do it. So I think I can squeeze it in here. So we have infinite sum. So let's see, all of the n's are becoming k's. So this is a k, this is a k. Hey, I'm in. So when n is 1, if you plug it in here, you would get k equals 0, right? Would that be right? 1 minus 1 is 0, so you start at 0. So you just take this number and you plug it in here and you get, I'll write it. So you see it, k equals 1 minus 1. So k is equal to 0. So that tells you to start at 0, okay? So you go to infinity. And then instead of n, we have k plus 1. So instead of c sub n, it's c sub k plus 1. And then instead of n, it's k plus 1, so parentheses k plus 1. Notice it's a little bit messy here, right? Be really careful. This is a subscript. This is not a subscript, right? And then here we just have x to the k. And that was the whole point, right? That's the whole point, right? Is we wanted the x to the k there, right? Then minus this 5, I'm going to go ahead and bring it in, and then you just replace all of the n's with k's, right? You don't have to do anything there. This will be the infinite sum, k equals 0 to infinity. Just replacing all of the n's with k's. This will be c sub k, x to the k, and all of this is equal to 0. Let me pause here and let you catch up. You know where the 5 went? It disappeared. So I messed up. It's points. It's good. Good. I'll write it down later. So it's good. Yep.
Why do we move it inside?
You don't have to. Yeah. It's weak. Okay. Yeah. No. Good. Yeah. It's bad. All right. So everyone okay with the steps? Any questions? I know it's a lot of notation on this one. This is a really good problem for like your in-class tests because you could do it. Like you could finish it. You'll see. I'll pass out the take-home test later today. You'll see some of the problems are like, whoa. You'll be able to do some of the take-home tests too. So that's good. Any questions? All right. So now they both start at x to the k. They both start at 0. So now we can combine everything, right, into a single sum. So this is going to be the infinite sum as k runs from 0 to infinity. Okay, 0 to infinity. And I'm going to go ahead and just combine these and factor out the x to the k, right? So I'm going to use a bracket. Just so bracket c sub k plus 1, parentheses k plus 1. That's that there. So those go here. Minus 5 c sub k. So that's why I put the 5 inside. You didn't have to put it inside, but it just makes it easier so you see it. And then we have bracket. Almost done. We're missing one thing here. We're missing the, what goes here? What's missing here? X to the k. Very good. I see how x to the k. Oh, and this is all equal to 0. Yes, Matthew?
For the second part, shouldn't k equals a negative 1?
No. We're here?
Yeah.
No, because all we do is replace k with n. So, are you thinking we have to like shift down or something? Or?
Right, if you put 0 in.
You put 0 in here. So k is 0. That's for the second one.
Okay.
For the first one, you put n in here, so you get k. That's the first one.
Oh, I see.
Yeah, good. Hey, Drew, all right. So far, this is exactly the same as last time, I guess, right? We haven't done anything new other than plug it into the DE. So let me just pause and let everyone catch up. So we're here. Let me erase this. It's not part of the problem. All right, so when you're here, this is equal to 0, right? So this is really key. So this is equal. You could think of it as 0 plus 0x, if you wanted to, plus 0x squared plus ... So this is true for all x, right? And these are somehow equal, right? That means all of this must also be equal to 0. So in the next step, all you do is you take all of this and you set it equal to 0, okay? So we have c sub k plus 1 minus 5c sub k. So every single time, right, when you get to this step, just take all of this and set it equal to 0, okay? And this is true for, it's really key, for k equals 0, 1, 2, 3, 4. So it's really important to write that down. It's not just like a formality like, oh, we should do it, otherwise it's wrong. No, if you don't do it, you might mess up, right? It's super important, right? This is going to help us like know what to do, right? Because it tells us to start at 0. This has a name. This is called a recurrence relation. If you go into like computer science, you'll study these. There's a whole there's a couple sections in a book where you study these. So I think, Jarrell, you studied these, right? Recurrence relations and discrete? A little bit, yeah. Okay, so we're here. So always just take whatever is here and set it equal to 0, and then it's for k equals 0, 1, 2, 3, etc. Now here's the trick. Always solve for the one with the bigger subscript, okay? Every single time, okay? So we solve for c sub k plus 1 because it has a bigger subscript, no matter what. So if you had like a c sub k plus 2, you would solve for that one, okay? So no matter what, always just solve for the one. So I'll add this. So we have c sub k plus 1, parentheses k plus 1. Again, watch out when you write it, like you don't mess up. Like this is a subscript and this is not a subscript. And that's equal to 5ck, okay, 5ck. And then we just divide by this. So c sub k plus 1 is equal to 5ck over k plus 1. And I'm going to go ahead and write it again. This is for k equals 0, 1, 2, etc. So stop there for a minute. So we're here. So no matter what DE you're doing, even in the other sections, like when we get to the harder ones, it's always these steps, okay? Even on the take-home, right? All the DEs, you always start them this way, right? You call it y, you take some derivatives, you plug it in, right? You do the stuff here. It could be harder than this. It will be, right, in some problems. This is a really good one because it's easy, and so it's like a good one for the test. Then you get here. Once they both start at the same number and they both have x to the k's, you can combine them, right? And then you're here. Then you set this equal to 0. And then you always solve for the one with the bigger subscript every single time. So any questions up to here? Now this is the beautiful part. Like this is like the part that's cool.
What do you mean solve for the bigger subscript?
Good question. So it's like, say you had c sub k plus 2, k plus 3, minus ck plus ck minus 1 equals 0. So you solve for this one, because k plus 2 is bigger than all the other ones. Mm-hmm. Yeah? Oh, no.
Oh, sorry.
What song is that? Oh, it's all right. Yeah. Yeah. I was listening to Epic Sax Guy. You ever heard of that? I'm sure you have. It's really old. No, you haven't? No, it's a meme. Epic Sax Guy. It's old. No, you know what that's about? Yeah. Dun, dun, dun. Yeah. You should look it up. Okay. Anyways, yeah, it's really old. So solve for the bigger one. Solve for the bigger one. Any questions? Any other questions up to here on this one? On this one. Okay. So now there's two ways to proceed, right? Well, in this way there's only one way, but in the next section there's two methods. There's the direct method, which is just plug stuff in and do it, which is what we're going to do. Then there's the indirect method, which is a little bit confusing, but I'll show you another day, right? So let's just plug stuff in and do it. So when you're plugging stuff in, be super careful, right? So it's really easy to mess up. So first we're going to plug in 0, right? So I'm going to write that down. So k equals 0. The reason I write it down is so I don't mess up. Okay, it's really easy to mess up. So when k is 0, you get C1. And when do you stop plugging stuff in? When you find a pattern, right? When you find a pattern. So we get 5C0, so 5C0, and then 0 plus 1 is 1. Okay, so that's all we get. So that's just 5C sub 0. Okay, you might say, what is C sub 0? We don't know, right? We don't know. To find C sub 0, we would need some type of initial condition, right? Like y of 0 equals 4, or something like that. Okay. Yeah. So, and then you just keep doing this until you find a pattern, right? So the patterns we're looking for in this class are e to the x, sine x, and cosine x, right? Like the Maclaurin series. On your exam, it will say, write in terms of familiar functions, so you'll know to look for a pattern. In fact, there's a pattern on every single question, so you'll know. Okay, so now let's plug in 1. So when k equals 1, we get c sub 1 plus 1. So that's c sub 2. Good. C sub 2. C sub 2. C sub 2. So that's going to be 5c1. So 5c1. Then 1 plus 1 is 2. So we get 2. then here's where the magic happens, right? We know what C1 is. C1 is 5C sub 0, right? Or physicists call it, what, C naught? So it's 5C naught. So, hey, you're leaving, Graciela? Huh? Yes. Bye. So this is 2. So then 5 times 5 is 5 squared. You might say, isn't it 25? Yes, it is. But we want to find patterns, right? So we leave it as 5 squared, C naught over, and check this out. 2 is actually 2 factorial, right? So we write it as 2 factorial. Yes, Matthew?
How did you get different values for k?
Oh, we just start plugging in these numbers.
So just start plugging.
Yeah, and it's really important, Matthew, to start with this one first, okay?
Would it be dependent on what k or n, k?
Yeah, this will tell you.
Okay, so like if when we found k down here to k equals 0, let's say k was 5. Would you start with 5 over there?
It depends on this here, right here.
This one.
Yes, this one, yes. But this one, the last one, yes. So, yeah, super key. On the harder ones, they won't be on the test. It's too hard. You will never finish. Like k would be 3, right? That's
Start over there with 3.
Yeah, that's really tough. That's really tough. Yeah.
So why did we just call it 2 factorial? Is there any particular reason?
Yeah, there is. There's a super important reason. So we're looking for a pattern. So we're looking for like patterns with factorials or powers. That's why. And on the take-home one, the patterns are harder. That's why it's a take-home, right? So look for patterns like with factorials or like 2 to the n. I think one of them is like 2 to the n factorial. That might be the pattern. So yeah, I'll pass it out today. So yeah. All right, let's keep going. So it's k equals 2. K equals 2. So when k equals 2, we will get C3. C3. So C3 would be 5. Oh, I almost messed up. K is 2. So it's 5 C2. Yeah, see how easy it is to mess up? Because you see a 3 here, and you want to put a 3 here, but no. K is 2, right? K is 2. So we have, K is 2. So it's 2 plus 1, which is 3. I almost messed up and did 3 plus 1, right? Because K is 2, so it's 2 plus 1. And then we know C2. C2 is here. This will be 5 over 3, and I'll replace C2 with this. I'll show the step. So 5 squared C sub 0 over 2 factorial. So you see it. It's beautiful, right? So just replacing C2 with what it is. And then you, again, you look for the pattern, right? So this will be 5 cubed.
C sub 0 over 3 factorial.
Over 3 factorial. Very good, Gage. 3 factorial. Yes, because 3 times 2 factorial is 3 factorial, right? 3 factorial is 3, 2, 1, right? 3, 2, 1. I think that's good. I think we see the pattern, right? The next one will probably be 5 to the 4, 4 factorial, etc. So now let's finish it, and let's finish it in a really elegant fashion. So any questions on this example so far? It's a really good problem because it's simple compared to some of the other ones, right? So, okay, so now let's do it. Let's finish it. So we started with this, right? At the beginning, Matthew said, why are we doing this? Why are we assuming this? The reason is we assume that the solution to this dE can be written in terms of a power series. So we assume it has this form. So this is the answer. This is the answer to the problem, right? We just have to find these, and then we can finish the question. So let's go ahead and write this down, and let's write it down the long way, like this. So y is equal to, so if you write it down the long way, it's C0 plus C1x plus C2x squared plus C3x cubed plus ... I'll stop there because we stopped at C3, but you could see, so you could easily write C4. So that's this, right? If you plug in 0, you get C0, you get C0x0, and then you plug in 1, you get C1x1, etc., right? Etc. Right? So we're just plugging it in. It's really beautiful to do it this way because you can see how it all falls apart. By the way, you can solve this problem in 5 seconds, and I'll show you how at the end. Yeah.
How did you get 5 squared and 2 factorial?
How did I get what?
5 squared and 2 factorial.
Oh, I don't know. Oh, this?
Yeah.
Oh. Yes, I plugged in C1. Very good. Yes. So C1 is 5C0. Then 5 times 5 is 5 squared. Good.
Okay.
You see it? No, good. And then you see how we got C3 as well, Matthew?
You plugged in C2.
Good. Yeah, good. Good ask. No, it's important. Good. This is a great test question. This is the only DE in this section, right? There was 2 DEs originally, but one was like really tough. So I'm like, no, it's just, you got to draw the line somewhere. So y equals, all right, so now what do? We just plug in what we have, right? This is really beautiful. So we have c sub 0 plus, and then c1, we know what c1 is, right? c1 is here, 5c0, right? 5c0. So this is going to be 5c sub 0 x plus. I like this stuff. I never learned this in school, so we had hurricanes when we were supposed to learn this, so never learned it. C sub 2, yeah, so that's why I like it better, because I had to like read the book. Like, C sub 2 is this, right? It's this. So it'll be 5 squared over 2 factorial c sub 0. So 2 factorial c sub 0 plus c3 is here, right? So it'll be 5 cubed c, yep.
You forgot the x squared.
Okay, gotcha. I'll get it after class. Thanks, Gage. Thanks. I need some caffeine. Oh, I left my soda. Thanks, Gage. Plus C3, so it'll be 5, thanks, Gage. 5 cubed c sub 0. So 5 cubed over 3 factorial c0. I didn't forget, I'm doing it on purpose. X cubed. Put it next to the 6 there. No, it's like, oh, what's wrong with him? No, all right. So we're here. Any questions? Any questions on this one? It's a nice problem. I like this problem. I like it because it's easy, right? Series are ridiculous. Wait till you see the next section. I mean, we'll start off easy. We're going to do today. Yeah, today we'll do 1 DE from the next section. I think we can do 1 today. Wait till you see it. You're going to be like, oh my God, it's epic. You've never done math problems this long before in your life. It makes it kind of interesting. It's like first time. So y equals, oh, what can we factor out from all of this? C sub 0, yes, beautiful. It's just rigged. So C sub 0, parentheses, right, parentheses. And so I'm gonna use some trickery here. So this is 1 plus, right, because we're pulling out the C sub 0. So then we have 5x, so 5x. Now this here, you can write this as 5x quantity squared. You might say, why would you do that? Because I'm looking for a pattern, watch. You can write it like this, plus 5x parentheses squared over 2 factorial. You see, you can combine the 5 squared and the x squared to do that, right? How do I know to do that? I'll show you in a minute, because I'm looking for a pattern. Plus 5x cubed over 3 factorial. Boom, dot, dot, dot. It's 3 dots, by the way, right? Don't forget the dots. Super key, right? Super key. The dots are important, right? It's an infinite sum. It goes on forever, right? It goes on forever. The reason I did this is because there is a function, right, that you might know. It's called e to the x, and it's equal to 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus dot, 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 right? That's e to the x, right? That's e to the x. So that's e to the x. It can also be written as an infinite sum, wish I was a little bit taller, like this, x to the n over n factorial, right? It can be written that way as well. So now you see here, you can write this in 2 ways. You can write it as an infinite sum, which I'll do first because the homework wants that. The homework wants the infinite sum form, right? So the homework wants it like this. So n equals 0 to infinity, because you always start e at 0. And instead of x, what do you think the value of x will be in this problem? Instead of x. So it's not e to the x in this case, it's e to something else. What do you think it would be? 5x, yeah. So this will be 5x to the n over n factorial, right? So your x is 5x, right? It's the same thing as what's up here, except your x is 5x. And this is actually c sub 0, e to the 5x. So the answer is just c sub 0, e to the 5x. That's it. That's it. That's it. So this is a problem where you don't really need series. You can solve this in like 8 seconds, maybe 10 seconds, depending on how fast you write. I'll show you how in a few minutes, right? In a minute or two. But there's some problems that you really have to use series, right? So like if we make it harder, you know, like if it was a y double prime and there was like x's everywhere, we might not be able to use what we learned before. So series are kind of like a last resort method for DEs, obviously, right? This takes forever, and this is the easiest problem. right? This is the easiest problem. The homework wants this. On an exam, I'll probably, on the take home, it wants both, right? I think on the in-class test, I just want this. So you can go from here to game over, done. Yep.
Do we have a table of e to the x and then
No.
the sums?
No, you just have to know 3 of them though. Just e, sine, and cosine. I know the homework has like ln and it has the geometric one, but for the test, just those 3. Yeah. Yeah, your in-class test is going to be really short because you only have 75 minutes. So I'm basically going to take the test I gave my other class and just make it even shorter. So you should be able to get 100 on the in-class. The hard part will be the take-home portion. I'll pass that out today. That's the hard part. But you can work together, right, on that. So make friends, stuff like that. Yeah.
Was the infinite sum given to us in the problem?
This here? No, you always start with this. Always. Good question, Rachel. Always. Always. You just always start with this. Let's go over it one more time from the beginning, and then I'll show you how to do it in 5 seconds. So you should always start off by doing this. Call it y. Always, no matter what. And this piece here, you take the derivative. So the c sub n is a constant, right? So when you take the derivative, the constant just hangs out, right? So you put the n in the front, and then you subtract 1, so you get x to the n minus 1. If you're wondering why it starts at 1, it has to do with the fact that the derivative of a constant is 0. If you plug in 0 here, you get c0 x to the 0. And then you add, you plug in 1, and you get this, etc., right? So here you just get c0 plus c1x plus blah, 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 blah. The derivative of c sub 0 is 0. So the 0th term goes away. It vanishes when you differentiate because it's a constant. So you shift up. The same thing would happen here. So if you took the derivative again, you would start at 2, right? Don't worry, there's not going to be a y triple prime. That's just too much, right, for a regular classroom situation. So we're here, right? So you take the derivative, you're here. You take everything and you plug it into the dE. So we had y prime. So y prime is this one, right? So that goes here, minus 5y. So that's here. And that's equal to 0, right? And then what you do is you call this k. So k is equal to n minus 1. Then you solve for n. So n is equal to k plus 1, right? So you're there. Here it's the same thing. You just k is n is k. Here this starts at 0, and the reason is you take this n here and you plug it in here. So 1 minus 1 is 0, so you start at 0. Okay? And this one's already starting at 0, so you're good. If this ends up starting at 1, it's like from last time. You have to make them both start at the highest number. We might do that later today. I'm not sure if we'll have time. But like if this was a 1, that's bad. That makes it harder. Then you have to plug in 0 here and start them both at 1. I think we did that at the end of class last time. That was pretty sneaky. That will come up another day probably. And then you can combine them when they're both x to the k's and you start at the same number. So you're here. Then you just take this and set it equal to 0. This is really important. I think Matthew asked about this also. This is key. This comes from here, right? From this piece here. That's really, really, really important. It's not just a formality, like, oh, if you get to write it, you lose points. Honestly, it's about getting it right because it tells you where to start, right? It's very important. And so if you don't know where to start, you won't be able to finish. So then when you're plugging these in, you don't have to write k equals 0, k equals 1, k equals 2. I do that so I don't mess up, because I will mess up, right? It's super easy to mess up. So carefully plug everything in. And don't simplify, right? Try to leave things unsimplified. Try to look for factorials and powers, right? And again, how do you know to do that? On your exam, it will say to find a pattern. It will say write in terms of familiar functions. It will say that. So you know it'll be e, sine, or cosine. All your exam questions will say, all the DEs will say write in terms of familiar functions, right? That way you can find the pattern during the test and get it right? There's some when their pattern is too hard, you'll see those in the next section. And for those, they don't even ask for a pattern. And then when you think you've figured out the pattern or you've come close, just write it out. Sometimes writing it out actually helps you see the pattern even more, right? So write it out, and then you're here. And then in this case, you see they're all positive, so it's probably going to be an exponential function. If they alternate, like if it's plus and minus, it's probably sine or cosine, right? And then you just rewrite it, and then we're there. So, any questions on this one? Do you want to see how to do it in 5 seconds?
Yes.
Yeah, check this out. So, this is so cheap. So, a long time ago, we were doing this thing. Well, I'll write it. Here's the DE. I'll even write the DE again. I can fit the whole solution in this little box. Watch this. So, we can write down the auxiliary equation. Remember that? So it's m to the 1. So just m minus 5 equals 0. For us, it was always 2 or higher. But you can do it when it's 1. And then so you just add 5. And then because we only have 1m and it's a real number, it's just y equals c e to the 5x. Game over. Done. Piece of cake. I know. I know. So why do we do all this? Because we're supposed to learn stuff, right? No. And because, right, it could be harder. You might not be able to use this method. So, yeah. So, yeah.
If we do that on the test, will we get full credit?
No. No.